We can use the equilibrium constant to solve for the equilibrium concentrations for all the products and reactants in a reaction mixture. Let's do an example. Okay, so we have some lanthanum carbonate and we're going to dump it into water until there's excess solid. So let's look at what that would look like. It'd probably be good to draw a picture. So we've got a beaker of water. We start adding in lanthanum carbonate, and some of it dissolves, but we keep adding until we get some excess solid down here that precipitates out. Notice we don't have to add very much to get that to happen because it's not a very soluble salt, right? This is a pretty small equilibrium constant. And let's show the equilibrium here, that we have a dynamic equilibrium of solid dissolving into the solution and ions in solution precipitating to form the solid. And of course, this is a dynamic equilibrium. It's going on all the time. But once we get to equilibrium, these two reactions, the dissolving reaction and the precipitation reaction, are taking place at the same rate. So there's no net difference once we get to equilibrium. Great. So we want to know, what is the concentration of this salt out here once we do get to equilibrium? Okay, so to do that, we have to remember what kind of equilibrium constant is a KSP? What reaction is attached to that type of equilibrium constant? So let's write out the reaction. It's the forward reaction for dissolving. So we're starting off with solid salt, and that is going to dissolve, at least to some extent, to give us 2 lanthanum ions, aqueous, and 3 carbonates. Okay, so you can tell that the carbonate is -2. You don't have to know this is a transition metal. You don't have to memorize its charge, because you can tell if there's 3 -2 ions, then this whole half over here has to be +6, and there's 2, so each lanthanum is going to be +3. All right, so we have our KSP and we have our reaction of interest, so let's solve this problem. One tool we can use, and it's a little bit overkill for this problem, but for more complex problems it'll be really helpful, is something called an ice table, where we look at the original concentrations that we have, how much those concentrations change, and what they are at equilibrium. And we're going to decide on what units we use. I like to put those right in the ice table, that we're going to use units of molarity since we're doing aqueous chemistry here. And we label this as being initial, change, and equilibrium, which is why this is sometimes called an ice table. Okay, so the initial concentrations. First of all, we want to talk about, this is a solid, right, the lanthanum carbonate. So we're not going to be plugging this into our equilibrium constant expression, so you can just cross it off. We know that that's going to end up being plugged in as a 1, or really just not plugged in at all. Okay, so let's look at these concentrations. Our initial concentration of lanthanum, well, if we go back to our problem statement, it says that we dissolved it in pure water. So there wasn't any lanthanum or carbonate at the very start. So we can write a 0 there. And then we see, how much does the concentration change for every mole of this that dissolves? We can see if we dissolve 1 mole of salt, we get 2 moles of the metal ions. So we'll say plus 2x. We don't know how much dissolves, so we're saying x number of moles dissolve, and this is going to be 2x. And we form 3 moles of the carbonate, so that's plus 3x. We know that we have to move in this direction towards the right because we start off with just pure water, so at least a little bit of the salt will dissolve before we get to equilibrium. At equilibrium, we're just adding our original concentration to our amount that we changed, so this just ends up being 2x, and this ends up being 3x. Then we write our expression for KSP. So KSP is going to be products over reactants. So for our products, we've got concentration of lanthanum. Okay, so we've got our concentration of lanthanum. It's got to be squared because we have 2 of those ions. Our concentration of carbonate, our concentration of carbonate, which has to be cubed, we've got 3 of those. Then we divide by the reactants, but since those are solids, we know that we don't include those in the Q or the equilibrium constant. Okay, so then we plug in these variables that we have on our ice table into this expression. So we said the lanthanum concentration is 2x. That entire quantity squared, so you've got to have the 2 and the x in there before you square it. And for the carbonate, it's 3x cubed. And this is where students often make mistakes. They take the square of the x and the cube of the x, but they don't do it to the numbers. You have to do it to both. So we get 4x squared times 27x cubed is equal to 108 x to the fifth. And now we can just take that expression and get our final answer. Okay, so now we just solve for x. So we divide by 108. So we've got KSP divided by 108 is equal to x to the fifth. So then we just take the fifth root of both sides. X is equal to the fifth root of KSP over 108. And if you don't have a variable root key on your calculator, you could just write this as KSP over 108 to the 1/5. Okay, great. So let's plug those numbers in. So x is equal to the KSP, which we said was 4.0, 10 to the negative 34th. And we divide by 108. And that is equal to 8.2 times 10 to the 8th. This number, since we're calculating concentrations, does have units. If we go back to our ICE table, we can see that we wrote everything out in molarity. So this is 8.2 molar. And that is the solubility of our salt in pure water. Notice that's not the concentrations of the individual ions. If we wanted the concentrations of the individual ions, we go back to our ICE table and see the concentration of lanthanum is 2x and the concentration of carbonate is 3x. So if we wanted to, we could come back here and say that the concentration of carbonate is 3 times 8.2 times 10 to the negative 8th molar. And notice this is a very, very small concentration. So this is essentially, this is around 25. So 25 times 10 to the negative 8th is about 2.5. So if we say that 3 times 8.2 is around 25, that's going to be 2.25 times 10 negative 8, or 250 times 10 to the negative 9 molar. So that's 250 nanomolar. So a very low concentration indeed. This isn't a very soluble salt. One final point, on all of these notes, we should be putting little subscripts on here saying equilibrium. And that includes on the expression we had back here. We should have equilibrium here and equilibrium here, because if we didn't specify that these concentrations were at equilibrium, then this isn't a K, it's just a Q. Okay, so make sure you write equilibrium subscripts on your expressions so that you're specifying that you're talking about K and not just Q. One final point, on all of these notes, we should be putting little subscripts on here saying equilibrium. And that includes on the expression we had back here. We should have equilibrium here and equilibrium here, because if we didn't specify that these concentrations were at equilibrium, then this isn't a K, it's just a Q. Okay, so make sure you write equilibrium subscripts on your expressions so that you're specifying that you're talking about K and not just Q.